All right. Good. So today we are going to do the generalized linear models. So this is roughly the end of the traditional statistics. And from next week on, we will getting into the modern territory. But yeah, so last time we talked about linear regression. I mentioned several times some of the things are already outdated, like the p-value model selection. We would talk about a better way of doing that later. But some of the things are still important, like the modeling concept. So we're trying to find a line or plane to fit all these data points. What's the meaning of all these betas? They're still valid. Later we'll introduce different methods to come up with these betas. The value of the betas may be different, but the interpretation remains the same. Right? So the important thing is the modeling framework and the interpretation of the outputs. Right? And yeah, that's not so relevant here. And today we are going to introduce a broader family of linear models. That's a so-called generalized linear model. And again, the same idea. The modeling framework is important. The interpretation is important. But the algorithm or the model selection, let's not worry about that, right? But it's good to understand how they do things, right? But that's no longer important. So we'll start by introducing logistic regression. So that's the regression kind of tool when we have Y being categorical. Right? Then we do the classification kind of idea in general. That's something we didn't emphasize last time. Last time when we do linear regression, we just go directly from X. We find a way to relate that to Y. That's just one step. Then we have a prediction and we're done. Today, the classification thing, we start with some features X. We will go to use that X to come up with some probability. But the probability is really not the last thing we want to say. Later we have the example about making judgment about a customer making a loan request. We need to decide, is this a bad guy who's going to default, or is that a good guy who is going to return the money? So our final decision is a yes or no kind of thing. But the model will only give us the probability. So we still have one extra step to go. So that's the class or the category. We still need to convert the class to the category. So there are actually two relative independent steps. And these two steps are sort of independent. Logistic regression is one tool to help us map from the X, the features, to the probability. Later we'll introduce many other tools. Or even k-nearest neighbor can be a tool to do the probability. But going from probability to the labels or class of each individual data point, that's another question. Right? And they're sort of independent. Then towards the end, we'll introduce other members in this family. On top of linear regression and the logistic regression, we also have other things like a Poisson regression, all these things. And they're all more or less can be fit into the same framework. You can eventually you will see that's just change one of the parameter in the R function, then you convert from logistic regression to Poisson regression. They are all nicely unified in the same framework, and that framework we call it generalized linear models. That's a big family. Right? So we'll just briefly introduce that, and that's not much technical details there. All right, so let's start from the question we talked about last time. Last time we talked about linear regression. We say actually we can represent the Y we're interested in by some mixture, some combinations of the features plus some noise, right? So the other way of seeing that we didn't talk about, the other way, the equivalent way of saying that is we're basically making an assumption on that Y the y variable is basically a normal distribution with the mean being all these combinations. And there's some variance, some noise on top of that, right? And that's basically the same way of writing here and the same way of writing there. And these two components actually nicely separated. All these x actually only contributes in affecting the mean of the y variable. And then there's epsilon is contributing the variance, the variability of that variable. And they are relatively independent. There are two things affecting two different parts. And when we do prediction, we actually use these mean as the prediction because we know the noise is not predictable. So using the mean is the best prediction we can have, right? And that's the picture we had last time. And the question, and last time we also spent a lot of time talking about different types of x. X can be a regular numerical value, can be a categorical. How do we convert that into dummies? And we can introduce nonlinear transformations. Then we can do the interactions. All these, we have a lot of tricks dealing with all kinds of x. But we didn't talk about other types of y, right? So far we have been talking about y has to be a number. It can be anywhere. According to this normal distribution, it can go from minus infinity to plus infinity. But in many, many situations, in the real applications, there are some kind of other types of y, right? Think about if we are predicting, like I said, the credit card default. We need to predict for each individual applicant, is this guy is going to default or not in the future, right? So that's a y. But y only takes two possible class or labels, right? We can change that to the numbers, but yeah. There are many things. We're trying to develop an algorithm to predict whether an email is a spam or not a spam. They call it ham. Also, eye colors. How do we predict the eye colors based on some other features of an individual, right? So you can see these are categorical, and the simpler ones have two categories, and the more complicated ones may have multiple categories, many categories. Right? So our eventual target is to predict y being one of the categories. Right? So that obviously doesn't fit into what we have been talking about. Linear regression doesn't work. Right? And there are more complicated ones, like what if y is a ranking? It's an ordered numerical value. What if y is a count? We're counting the number of goals in a football game. Right? The counts are like integers, first of all. Then this must be non-negative, right? Non-negative integers. This thing doesn't work. We cannot predict any arbitrary value for the number of goals, right? This is a count. Now we also have like a survival time. So that's about time until some event would happen. Let's predict the machine failure. What's the expected amount of time until the next machine failure, until the next customer complains, all these things, right? So that's time until some events happening. So this is not integers. Time can be a real number, but it's non-negative, at least non-negative. We cannot predict a negative time. So all these things are common in practice, but they don't fit into the linear regression framework because the y is not normally distributed, right? That's the question. So later you will see the big family of generalized linear model basically try to borrow the idea of linear regression and apply that idea to all these different kind of contexts. And the whole changes introduced are basically this guy. Instead of saying my y is a normal random variable, here I'm assuming the y to be a Bernoulli, head or tail, 0, 1, right? So I can basically manipulate the distributions. Here, later you will see we will do Bernoulli. You know Bernoulli distribution? Flip a coin, there are two outcomes. Then there's a probability coming with that. or binomial. Later we will do a Titanic data set. It says this kind of a person, there are 20 kind of passengers on the Titanic ship, and out of these 20, 8 died, 12 survived. What's the reason? Right, let's try to explain that. But this 8 and 12 are the observed value are the y's, and these are Bernoulli binomial random variables. We're not going to do ordinal. Don't worry about that. So when we do discrete count, this is essentially Poisson distribution. Okay? Distribution used to describe a count kind of environment. Survival will have exponential. And many other different ways. So generalized linear model is a big family. But the whole point is to generalize the linear regression idea such that we can accommodate all these different types of y, right? By changing the distribution. That's the whole point. And there's another side benefit here is related to the earlier observation. We said in linear regression, these x only affects the mean, but not the variability. Variability is independently controlled by some other things. But in practice, many times you will see the variability of y actually depends on some of the x. And how do we deal with a situation like that, right? So linear regression no longer fits into the context. Can we have a better way of doing that, right? That's the big picture, okay? Okay? Okay. So let's start with logistic regression. Logistic regression is the one dealing with categorical y. And in logistic regression, in this categorical context, there are basically two groups. One is when you only have two categories, so that's an easier situation. Binary classification. Then the other is a multinomial, more than two categories. That's a multinomial classification. And we would spend most of the time on binary classification because that's really the common problem. And multinomial classification, there's some solution out there, but it's not that popular. It doesn't work many times. So in reality, very often people decompose a multinomial thing into a many binomial thing, right? If you want to predict whether a customer belongs to one of the 10 groups, right? There are 10 possible categories this customer can fit into. You can have one big model to predict whether this guy is one of the 10. You can also have 10 individual models say, do this guy belong to group 1? Yes or no? So that's a binary. Do this guy belongs to group 2? Right? So you can decompose. So most of the tools, the analysis, the results are kind of centered around the binary classification. So this is the core of like in computer science, that's the core problem, binary classification. So let's take a simple example. We are predicting customer default. This is a credit card story. And we say we collect some X. So for each of the customer, we collect some information about this customer's annual income, credit card balance, that's how much money they owe to the bank so far, and whether they are students or not, right? Just trivial example. It's not real, but just simple example. And the why we need to predict is given this information about a particular customer, are these guys going to default or not? Right? That's a yes or no kind of a prediction. Right? So, and the natural question is how, if we go back to the history, check all the existing customers, we know some of them, we know they're X, and we know some of them eventually default, some didn't. Let's try to figure out what the relationship between this Y and X in our existing customers. Right? Then we have established something about X and Y, then we can predict future customers. Like I said, you can imagine there are two steps here. Going from this X, the first step we'll do the probability. So we are not going to directly jump to a conclusion, like given this is the income, this is the balance, this is the student status, this guy is a bad guy. We don't do that way. We have a middle step that is maybe with probability 0.65, he's going to return the money. Right? That's a probability. And going from probability to the categories. So we split that into two different tasks. Right? So we'll do that first one here. So let's plot the data. Right? So this should be familiar at this moment, this kind of a data representation. Right? So we have two different x, balance x1, this is x2, and the color indicates the y. Right? So this is the history. We have 10,000 customers in the past. Some eventually default, some didn't. I guess these are the zeros. These are the good guys. These are the bad guys. Once they actually default. Okay. This is no, this is yes. Right? So, do we have an existing method that can solve this problem? What? K-nearest neighbor, right? We only have that one. Linear regression doesn't work. All right? Linear regression actually works, but yeah. But k-nearest neighbor, we can actually do this, right? We have two continuous x. We have a y being categorical. We can find some neighbors and see how many neighbors are good guys, how many neighbors are bad ones. So we come up with a probability using that proportion, right? Good. And even without k-nearest neighbor, right? If you ask a 5-year-old kid, how do we split the blue color and the red color? The kid should be able to figure out. There's something there, right? There's some boundary. It's not perfect, but that seems to be the boundary. And people on the left are the good guys. People on the right are the bad guys. If you force me to guess, that's my guess, right? It's not perfect, but that's some guess, right? And another observation is it's not so important. Like clearly, balance is more important, right? Balance is more important than income. Because we say people on the left and people on the right, we are basically talking about balance. People with low balance and high balance, they behave quite differently. Income has less a mild influence on this, right? The vertical difference is minimal. So this can be seen by this. Before we do some analysis, this is a standard thing. Let's visualize this data in all the different kinds of ways. Let's try to see, are there any obvious patterns that we can eyeball all these things, right? So the first thing we do is, since we only have two variables, let's see their distribution. We say we collect all the good people, no default, and plot their balance distribution, right? So this is the box plots we talked about last time, the minimum, maximum, median, first quartile, third quartile, right? We talked about this last time. And there's some outliers. This is automatic by R. It just take out some outliers. But that's the distribution for the good people. And there's a distribution for the bad people, right? And there's a clear difference here, right? Good people and bad people are very different in terms of their balance, right? There's a clear. If I have to cut on this picture, I will cut somewhere here, right? Everything, if I have a data point with a balance below 1,300, I'll guess this is a good guy. Otherwise, it's a bad guy, right? So if it's not so intuitive, think about this distribution like this. Right? If you plot a histogram, you will have something like that. A lot of people, a lot of good guys having a balance in this range, a lot of bad guys having a balance in that range, right? So something like that. Okay? So that's the initial visualization. Actually, this is a trivial problem, so we don't need a lot of tools to solve that problem. But on the other hand, we just say income doesn't seem to play a big role here. The good guys and bad guys, their distribution of their income are roughly the same. It's hard to differentiate them by income. Okay? Okay. So then we need to have more standardized procedures. Even though this is a trivial problem, let's think about how do we come up with standardized procedures. Having whatever data I can convert to some predictions, probability predictions. Right? So the quick thought first is, since we already have the tool of linear regression, can we just directly borrow this idea, borrow this tool using linear regression? We just say, yeah, default is a yes or no. And maybe we just convert that to 0 and 1. And our y becomes numerical. Then we can solve that. Okay? Is there anything wrong here? It's just a number, right? Y just a number. It just happen to be, in this case, y only takes two values, 0 and 1. But they're still numbers, right? It works like this. Okay? Instead of having a point cloud, last time we have the point anywhere. Now we only have the points on the 0 and 1, right? So there are a bunch of good guys centered around here. And a bunch of bad guys are over here, right? So if you run regression, that's still a valid data set for regression. You can still run it. That's the resulted line. The blue guy is a resulted line. And what do we say about this line? What we want from this thing is a probability, right? Hopefully we want to say, if some guy with we know his balance is 1,500, this guy has a 20% probability of default, right? That's what we want to say. And the result is okay in this range. There's some number, and we can interpret that as a probability, right? What's the problem here? What's the problem? On the two sides, it doesn't work, right? It can be negative. On the other hand, it can go to infinity, right? So that's not what we want. We want, give me an arbitrary customer's profile. I want to generate a number between 0 and 1, not anything go beyond that, okay? So, but in practice, that's a valid solution, at least for now. It's a valid solution. It doesn't work on the sides. You can just, whenever this line hits 0, you just set that to 0, right? You can just do this way, and this thing goes like this. And that's still valid. That's going to work, but may not be very nice. And but the bigger issue is when there are more categories, then you cannot do that. You can convert binary into 0, 1. But when you have 3 categories, you cannot do 0, 1, 2. Right? We talked about this several times. So that doesn't work. So we need a more kind of a robust solution. It's not a good solution. And the solution is logistic regression. Right? And the key observation in the previous part of the analysis is all that we want is an output number that is in the range of 0 to 1. If you can give me a number in the range of 0 to 1, then I'm pretty much done. I can tune my curve in whatever sense, but I want to make sure the output is a probability. Right? But what's not nice is the regression doesn't give us a number in 0 to 1. It's minus infinity to plus infinity. It's a line. So we need a better mapping. And here by mapping, we mean, we call this signal. Later we'll do this. So this is the signal. Think about this as the credit score. So you collect all this information about this customer. You aggregate them by some weights, beta. At the end of the day, it becomes one number, some credit score. Right? At this moment, it doesn't have a meaning. But we really want to come up with a mapping. So if this guy has such a credit score, what's the chance of default? Right? We want to construct that mapping from the credit score to the probability. Right? Credit score can be anything. Right? And turns out there's a good solution to that. That's a famous logistic function. And this is the logistic function. Looks ugly, but but this is just the credit score, right? We have the eta. This is the same thing, right? Let's just add. We would just put the credit score into some sort of an exponential function, and turns out the output is perfectly in the range of 0 to 1, and we call that probability, the probability we want. Right? So that's how it looks like. Right? It's a nice S-shaped curve, and think about this is the credit score. Right? It can be anything, combination of all the x. Credit score goes from minus infinity to positive infinity, but at the end, the output is in the range from 0 to 1. Right? That actually solved the first piece of our challenge. We come up with such a thing. But then the next question is, does this guy represent the true thing? Right? Do we have the nice curve? Then we need to find an algorithm, use the data to calibrate all these betas. Right? After having all these beta right, theoretically, we should be able to find something to represent what we're doing. Okay? All right. So there are many names of the same thing. This is the logistic regression in machine learning. In statistics, this is logistic regression. In marketing, we call this the logit choice model. So they're basically mathematically they're exactly the same, but presented in different framework. So logistic regression is predicting yes or no. Right? For each customer, there's a chance of doing yes. There's some chance of doing no. And in marketing, people care about when the customer is facing a set of choices, like there's an iPhone 8, iPhone 8 Plus, iPhone 10. Which one you are going to choose? Right? So it's at the end, your choice is categorical Y. They want to figure out what kind of people will choose iPhone 8, what kind of people will choose iPhone 10, or all these things. Right? So that's X is about all these individual customers, and their choices is exactly these things. Right? This is about a choice model, trying to come up with a relationship between customers' choice and their characteristics. Right? Yeah. And next semester you will have the customer analytics or consumer analytics kind of modules. They will use a lot of logit. That's why they asked me to put it here, so just to make sure you know what it is. There's nothing special, right? Just the context is slightly different. All right, let's try to visualize that a little bit. So we just say we start with some credit score, eta. It's a linear combination of all these features. And we put this eta into this logistic function. Actually, we transform the eta into a range of 0 to 1, and we end up having a probability, right? Probability measure. And that thing can be, you can do one way and you can do the other way. So we just did going from eta to probability. And actually, you can do the opposite way. This is a one-to-one mapping, right? So you can inverse all these things. So you can map from probability to the corresponding eta, right? If this guy's default probability is this much, what's the corresponding credit score, right? There's nothing special. They just inverse the function. But they're different names, right? This is the logistic function. This is the logit function, right? And in the logit choice model, people still use this function, actually. Yeah. But one thing I want to highlight is this the kind of a central idea actually hidden here. We start with probability. Probability is in the range of 0 to 1, right? Let's think about the right-hand side. Right? We start with probability, then we end up having the credit score, right? So, but there are two operations. The first is this thing inside, and the next operation is a log. So what's this thing inside? What do we call this? Nobody knows. This is all out, right? This is the probability of this thing happen versus the probability of this thing not happening. Right? That's the odds, right? Let me make up an example. Like if we flip a coin, the probability of having heads, 0.5. Right? What's the odds? 1. Yeah? Or in the gambling market, we write that 1 to 1. Right? If you're gambling with me with the coin, this is 1 for 1. Right? If you win, I give you $1. If you lose, you give me your $1. That's 1 for 1. Right? Think about the dice. The probability of getting a number 1 is 1/6. Right? What's the odds? 1 to 5. Right? This is 1/5. Right? That's the odds. Right? This is when you gamble with people. That's the corresponding return. Right? But the whole point is not about probability and the odds. There's a 1-to-1 correspondence. Right? They carries the same amount of information, the same information. Right? But the point is, think about the range of the odds. What's the range of the odds? It can be 0. It can go all the way to infinity. Right? It's some super the kind of a high probability, low probability. You get very extreme situations. So this transformation basically carries the same information, but converts your probability into a different domain, 0 to infinity. Then we do the next log of odds. What do we have? So that's minus infinity to plus infinity. Right? That's the whole idea of all these transformations. How people design all this thing. The whole point is, at the end of the day, I have a number in this 0 to 1. I can find a corresponding number in minus infinity to plus infinity, or the other way around. Right? Okay. So that's a transformation. So we end up having a transformation. That's nice, 0 to 1. And that's the final model. According to logistic regression, that's going to be our model. Our input is a bunch of x. We would combine this x into the credit score. We put it into the logistic function. The output is a probability. That's a probability we want to predict, probability of default. Right? And the question is, how do we find the optimal beta 0, beta 1? How do we find the estimate? So it turns out there's a slightly more complicated way of getting that than least square. So last time when we do regression, we said least square is just an explicit formula. Give me your data, I just put in to the formula, get a number. This is slightly more complicated. You need to iteratively find the optimal. But let's not worry about the algorithm. It's built in the software. Right? Give me the data, it's guaranteed to find the best beta 0 and beta 1 represents this relationship. And that's going to be the final model. Okay? You good? If you want to know the algorithm, I have notes. Last year I taught that, but not many people understand, so I just took it out. Yeah. So let's not worry about the deep in the core how the algorithm is solving that. But give me the data, give me the structure of the model. I can find the coefficient, the parameters. Next, let's see how do we do that in R. Right? So I've mentioned this. From now on, all these different models, they all use the same type of language, the same sort of format. Right? Last time we did LM, stands for linear model. This is a GLM, generalized linear models. Right? This is more general, but still in the same sort of format and grammar. So that's the command we run logistic regression. GLM is the function. We said we still have to specify what is your data, what is your model. This is our model. This is Y. This is X. Right? That's all the same. The only thing special is this guy. Because GLM is a big family of different models, you have to, it's a family of families. Now you have to specify the family. But there's a collection of multiple different tools. it tries to unify all these different tools in the same framework. So whatever tool you run, the output is similar. Right? That's a nice thing. But here we are running a binary logistic regression, so we have to specify binomial. Binomial is the family specifying the distribution of y. Right? Earlier we said for linear regression, it's Gaussian. Right? And yeah, if you don't specify this family in GLM, the default is Gaussian. So that's basically exactly the same as linear regression. The default is Gaussian. We're not doing Gaussian, so we do binomial. That's related to y. This is a binary classification. So whenever you're doing binary classification, your y is a 0, 1 kind of thing. So that's a binomial. Right? And then in the middle, so this is the first piece of information. Family is a binomial. In the middle, you have the link being logit. That's the link logit. Where's logit? This is the logit thing. So this is somewhat an arbitrary way of mapping the credit score to a probability. Right? Later, we'll introduce many other ways of doing that. So this is one of the most popular ways, just because it's easier to solve. And this is a so-called logit link. There's no particular reason why, but we are using the logit, the mapping. Right? There are several other ones, but this is really the default. So if you're lazy, you can just delete things in the middle. This is the default. Whenever you specify binomial, the default is logit. So logistic regression is that. So this piece of information says we are using logistic regression. Actually, both. So binomial and the logit link collectively makes this thing called the so-called logistic regression. All right. So that's how we start this thing. And then we have a very similar set of information like we have in linear regression. Okay? There's some change of the names, but they're the same thing. This is about the residues. What was the name in linear regression? Just residues, right? So here we introduce a new concept called deviance. That's important. Deviance is basically a generic error measure. So we can measure the error when y is Gaussian, when y is binomial, when y is Poisson, anything. So the whole point here is we want to have a unified framework. And deviance is exactly the residual sum of squares, something like that, no, residual in linear regression when this thing is Gaussian. That's a special case. But just to make sure everything is consistent, they use a different name. So for now, just think about this is the residual. We'll talk about the definition of deviance later. This is a bit heavy. Just to make sure different models can be described in the same actual measure that we come up with, let's say. Then we have the coefficients. Do we spot any difference? Anybody spot any difference? Z, huh? We're talking about z value, not t value. Z. Right? T is a direct result of the Gaussian assumption. We said when the noise is Gaussian, when we fit all these things, we get the betas of following a t distribution. Right? That's what we talked about last time. But in the general case, in general, we don't have a distribution for the betas in this context. So this is an approximation. This is an approximation. So somebody proved when your data goes large enough, all these beta coefficients are asymptotically normal. So they can use normal distribution. That's not that important. But for us, the important thing is interpretation. Interpretation stays the same. Nothing has changed. This is asymptotic. What? when your data is large enough, all these estimates are normally distributed. It depends on the algorithm. So we didn't talk about the algorithm, so that's not there. But don't worry, the majority of the things are the same. Right? Let's ignore this thing. That's not important here. Then the error measures. Okay? Earlier we just said that deviance is somewhat like the residual. And in linear regression, the first error measure we talked about was R square. Right? R square. R square is a percentage kind of a measure. The total error without a model versus the error we have a model was the percentage difference. Right? But in the generalized world, we no longer have that percentage kind of a thing. So what we have is two numbers. So this is a null deviance. So that's a total sort of error when you don't have your model. So you use the average kind of idea, right? So that corresponds to the total sum of square in linear regression. That's when you don't have a model, you don't have an X to explain what's going on. And this is residual deviance. That's the remaining error, just like the RSS. Right? And in linear regression, we can just take the ratio and it's a percentage thing. But in generalized linear model, we cannot do that. There's some gains and there's some loss, but don't worry about that. But keep in mind, these are in-sample measures, so they don't matter too much. It just shows how this S-shaped curve fits your data, how good it is. Right? Okay. Then the important thing on this part is this AIC. I'll show you the definition later, but this guy is really corresponding to the adjusted R square. It's a minus adjusted R square. In adjusted R square, the larger the better. Right? This guy is still an error measure. The smaller the better. Let me write it. So this is an error, but it's just like adjusted R square combines the R square information, like what we have here, with the number of predictors, how complicated your model is. Combine the two things. AIC also combines the residual deviance and the number of predictors. And actually, there's a trivial formula. AIC is just this number minus plus 2 times the number of predictors. Number of parameters here. Yeah, here is 2, including the intercept and the beta 0 and beta 1. Okay? So we have 2. Right. So when we run a generalized linear model, AIC is, at least on this page, AIC is the most important number. So that tells you how good is your model. Right? But the problem is AIC is not in the sense of percentage, not like an adjusted R square. Then with R square, adjusted R square, we can compare different models. This model has 90%. This model has 20%. So this sounds like better. But AIC is an absolute number. That's the total error. So you cannot compare the AIC across different models or different data. But with the same data, you can still compare. With the same set of data points, you can compare different models. Right? So that's the final number indicating how good your model is, right, in this case. So it's no longer that in-sample. So that's a combination of the in-sample error and the number of predictors, just like adjusted R square. All right? So these things are not going to be important in the future. Important things are the meaning of these betas and the structure of the model. When we say something like this, what do we mean? Right? There's the model in the previous page. Yeah. There's also some information about the underlying algorithm, how many iterations it takes to find the optimal beta. It's not important. Right? That's the output. That's the output of the model. Given the best fit, beta 0, beta 1 here, we can plot the model output. Right? So remember earlier we have a linear regression fit that goes to negative and infinity. But this guy is going to be the S-shaped, and this is going to be in the range of 0 to 1. Right? So that's this is linear. This is logistic. Okay? So let's try to make sense of this S shape. So this is the best fit, representing what, the black points. Those are our data points. Right? We have 10,000 customers. So think about this region. What do we say here in this region? These are the people with super low balance. What's the prediction here? Their probability of default is almost 0. Right? So that's also related to the data. Think about how there are many black points in here, but there's nobody in here. Right? So these are the people with low balance, and with this guy in this range, there's no default at all. Right? So that's why it says 0. Basically, in this range, the probability is 0. Right? Think about this range. Now think about this range. Right? Say 1,300 to 1,700. So in this range, we have different predictions, like 1,500 is this number, 10%, for example. Right? It says if someone has a default, have a balance of 1,500, according to this model, the default probability is roughly 10%. Right? And if you look at the data, it's actually, so this 10% is fitted according to this data, right? So in the history, what do we see? In this range, the majority of people are good guys, but we are starting to see some bad guys, right? And this proportion is, this whole blue curve is fitted according to this proportion in some sense, right? And similarly, in this region, we have everybody being bad guys, right? Probability is close to 1. They're all bad guys. That's also in line with our experience. Okay, so that's the best S-shaped curve that fits all these proportions in each bin. Right? Think about things like that. All right. So then the interpretation. That's a visualization of the resulted model. Interpretation. We need to look at the beta coefficient. Just like before, given the coefficient number and the significance, we can make up some stories. Right? So we say if beta is 0, it's basically say insignificant. Right? So if according to the model, this beta, the coefficient with respect to balance is not significant, then we say, yeah, default and balance has no relationship. Right? That's natural. But on the other side, the things we can say is less than in linear regression. Here we can only make some directional kind of a conclusion, not really proportional. Right? In linear regression, it's proportional. Every $1 you spend, you get one more customer in your shop. All these things. But here it's not linear, so not that easy. So, but the only thing we can say is a positive or negative. If it's a positive, then larger x leads to higher probability. If it's negative, larger x leads to lower probability. Right? So this part directional. Okay, but the exact magnitude we cannot just say by checking the beta. It really depends on where your beta is, right? If you look at the picture here, if you want to say for every extra $100 in your balance, what's the changes in your default probability? Here, there's virtually no change. But here is super sensitive. Right? Here, there's no change again. Right? So it really depends on where you are. And also, you can see the S-shaped curve would highlight a region where this probability changes very fast. And there's some other regions on the two sides, the probability barely changes. Right? So there's a sensitive region, there's an insensitive region. Okay. Then with that model, we can do all kinds of a prediction, just like in linear regression. We just plug in the x, right? So we said that we have a new customer with a balance of $1,000. What's the default probability? So this is our model, right? This is our model. That's what I mean, the logistic model after training. Right? So we just plug in the 1,000 number, and we get a probability. I can do that for, yeah, it's less than 1% for somebody with a $1,000 balance. So we can do that $2,000. You plug in the number, it's going to be much higher, right? So we just say $2,000 is the sensitive zone, right? Now it's going to hike up. Okay, so that's the logistic model, right? Give me an x, I can give you a probability of default. Right? So there are several other variants of this data set. What are we doing here? We're doing default versus students. Right? Earlier was default versus balance. Now we're doing students. Just quickly, let's try to do a quick interpretation. Right? Student is a binary, categorical variable, yes or no. So what do we say here? What do we say here? Oops. It's positive. It's significant and positive, right? Therefore, students are more likely to default, right? Okay. So we don't know by how much, but students are more likely to be default because this is positive. Okay. Mm-hmm. And if you really want to know by how much, you have to plug in the numbers. Right? Students being yes, so you have a 1 here. Student being no, you have a 0 here. So you plug in all the numbers, you can see the probabilities. Right? On average, students is 4.3%, non-student 2.9%. Right? That's kind of things. If you want, you can do all these things. And you can do a massive model with all the features. So in this data, there are all the 3 balanced income students. We just throw in everything. What do we find here? Income is not significant. That's okay, right? Like just at the very beginning, we visualize that picture. We see income probably don't say too much. Right? How about the other things? Student? Yeah? Why? Huh? So what's the difference here? Let's ignore income, right? That's not a significant one. Let's ignore income, right? Earlier we just tried to figure out the default versus students. Now it's default versus balance and students, right? By including the variable balance, we find out balance actually is a better variable explaining a lot of the variability. And after controlling for balance, students tend to be better, right? It's negative. So being students, given the same balance, right? Earlier we didn't try to differentiate. Now we say if you have the same balance, a student is less likely to default. Okay? That's the difference. Right? Earlier was just general comparison of the student and non-students. Now we're saying for the same balance, let's compare student and non-students. Okay? So this is a fair comparison. Right? And if you're curious, you can compare their AIC, which one is a better model. I think it should be this one. Right? This has 2 significant variables. Okay. Now you can do the prediction. That's the full model. You can plug in everything and do a prediction. That's not a another point. So let's do a little bit extra on the deviance and AIC. This is important thing in the whole family, not only for logistic regression. Right? We said the deviance is sort of the error measure. We have the formal formula here, the definition of deviance. Don't worry, that's not the point here. First of all, it's a measure of badness of fit. Right? So it's an error. The smaller, the better. Right? And the troublesome thing is in linear regression, when we have some error, we know like by including more variables and more variables, eventually you can explain pretty much everything. And the minimum, the best you can achieve should be 0 error. Right? In linear regression, just think about the ideal situation should have a 0 error. But in generalized linear models, we don't have the 0 deviance kind of a context. So the best you can achieve depends on your data or depends on your model, depends on many things. So actually, that's the best we can achieve. So whenever we're talking about the quality of the model is the error measure, log likelihood of that model relative to the best you can achieve. It's just because the reference point is fluctuating. Not like in linear regression, the reference point is always 0. And you can just talk about the one number. Here, everything is fluctuating, so you need to talk about the difference. But that's not so important here. Just keep in mind this is a badness of fitting and corresponds to the residual. Right? Then we have the AIC we have seen several times. The full name is this Akaike information criteria. This is a Japanese name, Japanese statisticians. So he just designed this measure. He said, I believe this is a good measure of model, the fit of the model. Right? So we use the S-shaped curve to fit that model, other data. So the definition is like the first part is the same. It's the measure of the fit, goodness of fit. Take a negative, so that's a badness of fit. But then it has the P, just like adjusted R-square. We put the number of predictors into this picture. There's no particular meaning. You just say, I need to take the number of predictors into account, so I just put a P there. Yeah? So let's, and it turns out to be working well. So everybody's using that. Right? But at the end of the day, it's also a badness of fit, so it's an error. And it's similar to the adjusted R-square I mentioned, but it's just an absolute number. Right? It's not a percentage. Because we cannot measure the percentage, we don't know the best. Where is the best? We don't know that. Okay? So these won't be important in the future, but that's what people use in. Okay, so then we have several kind of little details we need to worry about. First thing is when we do classification, binary classification especially, there are 2 types of data we may encounter. The first type of data is nicer. It's the credit default data we have been talking about earlier. The first column is the Y taking value yes or no. Then the rest are X, student balance income. Right? That's an important thing here is every row is one customer. Every row is one customer. The customer eventually default or not default. Right? So that's a nicer situation, an easier one to work with. And the other type of situation, later we'll talk about this data set, is like a good example is the famous Titanic data. This is the shape of the data. So the Titanic data set captures among all the passengers on that ship, who survived, who didn't survive, right? But they don't have many features about these passengers. They only have these 3 features about which class of the cabin they're staying in, the sex of this passenger, and the age of this passenger. And all these are categorical variables. So in that sense, they have a lot of repeated data points that having the same features, right? There are definitely multiple. In this case, there are 5 people staying in the first class, they're male and they're child. Right? So there are 5 such data points. They have exactly the same features. So in that sense, we have to group them. So we cannot have the same X. So we group them into a grouped data. So we group the people with the same features all together. We say there are 5 of them. Out of these 5, all the 5 survived. Right? Like here, the first class male adults, there are more than 100 of them. These many didn't survive, these many survived, right? So essentially, this is X, this is Y. And we're having 2 Ys there. Yeah? So this is a Bernoulli data with some probability, right? So Bernoulli is a coin flip. Every data point is a coin flip. You have a yes or no. This is a binomial data. Binomial data with N and P, right? This is we flip the coin 5 times, and out of all the 5 times, we have 5 heads. Right? That's what it says, right? But at the end of the day, we're talking about the same thing. Every individual has 1 probability to be survive or not survive, right? So logistic regression can handle both type of data, but just be careful when you do this kind of things. Right? And another thing is when you group things together, this becomes 1 data point. Every row is 1 data point in the logistic regression. Later we'll show, because they all have the same X. If they have the same X, you cannot have multiple points later. So after you group, this is 1 data point, right? Not 5 data points here. This is 1. Okay? So that's the 2 types of data we often see.
So when you're doing a model, does it treat each data point with the same kind of weightage?
Yeah.
Or is it somehow
Yeah.
accounting back the...
There's no weight. There's no weight. It just treats everybody as 1 data point, but the size makes some difference. Definitely, here you're only talking about 5%. Here you're talking about more than 100%. So that makes some difference. But eventually what we are trying to say is how likely are first-class male adults survive? Then the size is not that. So for each data point, basically you want to predict 1 probability. For people in that group, what's the survival probability? So it doesn't matter that much in that sense. Yeah. Yeah. No. So depending on your question, the question here is for people in this group, what's the chance of survival? Then each group is assigned the same weightage because we are treating each group as 1 data point. If your question is about what is about a randomly picked person, what's the survival probability? Then that's different because there are more adults and there's less child, and that's different. Right? Here is all about the unit of analysis is the group. We only have these different types of groups. Yes, exactly. So you cannot further split them because they are all the same according to your data. Right? So that's let's just focus on the groups, right, in that sense. Yes.
Can you still get a similar result?
I don't think you can run that. You can try. You cannot have the 2 X being the same. The matrix will fail. You cannot have the same thing on the same row.
If you make them just very slightly different, would it fit sort of a similar curve?
No, how do you do that? These are all categorical, right? These are not numbers, so you cannot perturb them, right? This don't happen that often because often you have many ways to differentiate all these guys, right? But this is really limited information. In today's homework, you will see similar data sets, right? Just to give you an idea what it's all about. Right? But that's not a common thing. Yeah. All right. Another kind of a challenge in binary classification. This is not limited to logistic regression. This is a big challenge to all the classification problems. That is the imbalanceness in your data. So we say we want to have a data, we have 10,000 customers. Ideally, we want to have 5,000 good guys, 5,000 bad guys. So we can have a head-to-head comparison. That's the ideal situation. And the more balanced your data is, the more accurate or the less biased the beta you will have. But in reality, many real data, the smaller proportion of bad guys and the majority of people are just good people, right? In this default data later you will see, out of 10,000 customers, there were only 300-something default cases, right? So that's 3% of default on average. That creates a big challenge. Think about the big challenge is this problem sounds like a trivial problem because if you just predict everybody to be good guys, what's your error rate? 3%, because there are only 3%. So your accuracy can be 97% without doing anything. So that's a pretty high bar sitting there. So that's your norm model. Without any information, that's your norm model. And you need to tell your logistic regression to find a model that beats the norm. And very often you just give up. You just say, let's just predict everybody to be to be good. That's pretty good enough, right? And that's not limited to logistic regression. Almost all the classification problems, you will have such challenge. And the nice thing is there's some heuristic way of solving that. In general, people say logistic regression or in general binary classification works well when the ratio is up to like 5 times. 5 times, so you have 1 bad guy, then you have 5 good guys. If it's more than that, if the imbalanceness is more than that, you are having trouble, right? It's a rule of thumb, not really theoretical. But if you don't have that situation, if your data is more imbalanced than that, you need to think about what to do with that. So if you only have 3% of the bad guys, 97 good ones, that's too much. So the idea is the so-called case control sampling. I say, I don't have many bad people. Let's keep all the bad people here. I have too many good people. They are, in some sense, redundant. I don't really need so many good people. So let me take a subset of that, right? Let me shrink the good people to some extent that it's more balanced. Right? I have 3% bad people. Let me keep 15% of the good people. So that's 3 to 15. That's 1 to 5. Right? So I'm shrinking that good ones. So that's the idea. That's pretty general. We do that almost all the time. But you may wonder, of course, that you can fit your model, but your conclusion may be very different, right? You're taking out some of the data. Before your belief is there are 3% bad guys. Now after shrinking the data, your belief is there are 20% bad guys, right? It's very different. It turns out for logistic regression, there's a nice property. Whatever you do by changing some of the number of the data points in some of the cases, the betas are not going to be affected. All the coefficients with respect to your features are not going to be affected. This is only for logistic regression. You can prove that. The only thing being affected is the intercept, beta 0. Because before your belief is 3%, now it becomes 20%. That thing is really beta 0. It's not related to the impact of balance or students and all those other things. So only beta 0 is affected, but turns out there's a nice formula. You can just fix that. After doing all these data changes, you are introducing some bias, but there's a formula to fix that. So let me explain this fix. So this is the beta 0 from the reduced data. Right? So after you reduce the data set, you can run your logistic regression and get the beta 0. Right? That's the one you get. Right? That's not the true one. We all know that. We want the true one related to the biased one, but we need to fix that according to this formula. And that fix depends on the two pi and pi tilde. Pi is the original proportion of yes. In our story, that is the 3% we're talking about. Originally, in your data set, there were only 3% of ones, so that's the 3%. Right? Just a number. Before you start, check through your data set. That's a 3. Pi tilde is the proportion of one yes in your reduced data set. Yeah, I reduced that to 15%. Right? Is that 15? 3 versus 5. No, it's 1 to 5. Let's just say 20%. Right? So I have 1 copy of bad guys versus 4 copies of good guys. Okay? This was 3%. This was originally 12%. So I'm only keeping that amount of data. Right? So the ratio of bad guys in the new data set is 20%. Right? Okay? So before we have 3% of the bad guys, we don't touch that. We have 97% of the good guys. So we reduce that 97 to 12. Right? We have 9,700 good ones. We only keep 1,200 sitting there, such that our ratio is 1 to 4. And that's the formula. Only for logistic regression, that's going to work. And that's the number one challenge in classification and balanced data. Very often you have that. Think about this is credit card default, 3%. It's already pretty high. Think about those guys predicting what kind of customer will click my online advertisement. The click rate is like 1 out of 10,000. Right? So how do you predict who is going to click that? That's very difficult, just because of the balanceness. And that also has some big implication on experiment design. In the past, when this is also something made logistic regression famous. In the past, when people study like a cancer problem, so they will follow this different. They call some volunteers. Like I get 100 volunteers, so I follow them for 20 years. I keep track of their life behavior, everything, what they eat, how much they sleep, how much pressure. Then I say, observe this for 20 years. Hopefully some of the people among this 100 get some cancer. So I have a data set, right? So I need to do this. But out of this 100, maybe there's only one guy get cancer. How do we figure out what's the driver? I have the data about all these 100 person for 20 years. But if there's nobody having cancer, then my experiment is done, right? And I cannot say, let's follow 10,000 customers, 10,000 volunteers. You cannot afford that, right? That's just impossible. So that's the traditional way. Without this thing, that's the only way you can do, right? You come with a set, some becomes 0, some becomes 1, then you figure out why. But with this case control sampling, you can do backwards. You say, now at the hospital, I have a bunch of people who are having cancers. I'm measuring whatever characteristics. Then I'm collecting another group of people without cancers. By just comparing them, I can do something, right? So you can do backwards, right? That's there's some extra work on that. This is pretty famous in medical trials, all this case control sampling. Okay. Right? Okay. There's some other tiny technical issues. Sometime later you will see. We don't see that today, but in the future you will see that. When you fit a logistic regression, you get a warning from R. It says that the generalized linear model fits this fit is a probability of 0 or 1, something like that. So this is driven by a happy technical problem. The happy technical problem is like whenever you do logistic regression, you're expecting some of the good guys and some of the bad guys somewhere, right? Ideally, and you want to have some overlap here. So in some region, there's some proportion of good guys and bad guys, right? This is my X. Think about the balance. You need something. Therefore, you can fit your S-shaped curve. Right? That's the requirement. But in some unfortunate or maybe fortunate situation, your data is actually separable. So there's no overlap at all. If there's no overlap, it's very hard to fit one S-curve to this data because there are many possibilities. Right? I can fit an S-curve like this. I can fit an S-curve like this. I can fit like this. Right? My data cannot differentiate which one is better, which one is worse. So you get a warning like that whenever you have that situation. But this is a happy problem, right? Your data is separable. You can use some different method. You just easily have a clear cut. So that's not an issue. Or sometimes you can just ignore that. If your objective is to predict something, who cares about all these three differences? If I'm just predicting, I can always perfectly predicting people showing up here and showing up there. Right? The troublesome thing is really the beta. Think about this as a balance. I may have very different beta with respect to balance in these three different models. If you want to make up stories about beta, then this is an issue. If you're just predicting, doesn't matter. Well, who cares? Yeah. So most of the time when we do prediction, we just ignore all these warnings. Doesn't matter. Yeah, and the imbalanced thing, we talk about that. The more imbalanced, the more bias. You can fix that, but still there's some variance, all these things. It's a troublesome situation. At unbalanced, there are two types of unbalanced. Right? There's a happy situation. You might have 1,000 ones and many zeros. That's okay. Just reduce your zeros. You still have 1,000 ones there. Right? This is okay. There's some situation you have 2 ones. You have 98 zeros. This is a pathetic situation. If you have 2 data points out there, there's not much. No matter how you shrink, there's not much. Right? So that's both imbalanced, but it really depends on how many data points you have on a smaller situation. Right? The 1,000 is way different from 2, right? In that sense. And we are pretty much done with logistic regression. We didn't talk about the multinomial situation. If you want, there's a package doing the multinomial, roughly the same kind of idea. But multinomial is not that common, right? Or popular in that sense. And multinomial is very hard to, later we talk about measure the performance of the fit. Multinomial is not easy. Right? Let's leave it on the side. In the future, if you need to do that, we can talk about that. Let's have a break first. Okay, let's have a break first. So we're done with the logistic regression, converting X to probability. The next step is having this probability, how do we make the next step of prediction? Okay? Categories they should have 3 probabilities. The output is 3 probabilities. Output is 3 probabilities. Yes. multinomial logistic regression. Give you 3 probabilities.
So you have
So for each customer, you have 3 different colors. Every customer can take
probability of having one color, let's say 90% and 10%, like,
yeah.
I see.
Then eventually, which color you predict? That's
So
another
you will
question.
have, because if you have 2, you only need one equation because it's either this or the other one.
Yeah.
Or you have, let's say 3, you'll be having 2 equations. Is it?
Yeah, sort of.
2 equations. So because 1 minus the 2 will give you the last one.
Yeah. That's probably right. Yeah.
So, for this one, just now you give example which will be used in marketing, right?
Mm-hmm.
You can decide how many can you buy or how can you decide? Because this is from minus.
No, they use this whole model.
No, this is
this one.
Oh,
Just say the customer's income, the customer gender, what's the probability.
So they are using this one too.
It's the same model.
Okay.
Same model.
One thing is just like here you see, I think the presentation is with the same balance, the student will be have a chance to before, right?
Yes, controlling the balance.
But why we don't say being student the balance more, if they have a more balance they are going to
why not? You can say that.
so we can say
So,
way, right?
yeah, controlling for the students.
Okay.
There's more balance leads to more default.
Oh,
right?
okay. I just want to see this case sample sampling. If we don't do the case sample sampling, what will happen? Let's say we really have a very unbalanced data. We are just running.
Very often you just predict everybody to be zero.
Oh, okay.
And you basically don't have a model.
Okay.
It may not be able to find a model that's better than that. So it just
with regards to the question, so because you say you do case control sampling, but the beta is not change except for beta sample.
yeah.
So, but if beta not changes, then essentially this will change. So,
Yes. Yeah. Sorry.
So then what's the purpose of this equation that measures back to the original?
There's a proof that it's a long proof, but it didn't put it there. But you can show that that's how you fix. But in order to understand, I think the better way is you can open up this. You can see if you divide by exponential to the power of greater than 0, divide this term, divide by this abstract term. So that term only contributes in terms of changing the base. Okay. Right. So basically, initially we have 10,000, and then we soon start to 9,000. That's basically.
When do you do the calculation?
When the rate of the less common one is less than 10%, roughly less.
Thank you.
Yeah, some people say 5%. If the number 1 is less than 5%, so definitely need to find rule of thumb. You just combine them together. In our code, the family is binomial, right? So that's binomial and Bernoulli are the same. Bernoulli is a special case. No, you don't. As long as the outcome is binary.
So even if you choose the amount like even I do
Yeah.
the whole thing.
Yeah. So binomial, Bernoulli is a binomial when you try once.
Oh, so you try.
That's a special case. Yeah.
Then the other one you mentioned you use the formula to use calculation of exponent. If I use the model, once the model is exponent, that's when will that be
That would be the cost.
Exactly. Yeah. The fitted value and also the prediction.
That would be the cost. And the third thing you mentioned, when you build out I mean, in this case, it's not balanced, and you can build up from not sufficient to study aspect. Is there any rule of thumb, how many data points should be required?
It really depends on how many features you have.
How many features?
Yeah, how many X you have. If you have a simpler X, just have balance. That's the only thing. 10, 20 data points would be enough. Yes, but in general, we have in general, we want the data to visit N. This is P. How many columns? In general, N should be larger than N has one. So you have 5 columns to be about 50 data points.
That's a rule.
Rule of thumb. So it's like that. And we are saying a lot of big data situations, these things go crazy, but we will have that's the problem. Yeah. But data for regression, later we find each business rule, even you have so many people to make a choice. Make a choice based on data. For example. Okay. So let's continue. So the next big question is, after we have the logistic regression predicting all the probability for each data point, how do we label this guy as a bad guy or good guy? Right? That's not a trivial task. And again, this is independent of the first step. How did you get the probability prediction? You might have some k-nearest neighbor to generate your probability prediction. You still need to do this step. Right? So let's think about last time when we do k-nearest neighbor, we actually use this. We say k-nearest neighbor give us some proportion among the neighbors, 15 neighbors, how many are blue, how many are orange, all these things. And we use that as a probability prediction, and we use 0.5 as a cutoff. Everything above 0.5, we predict that as 1. Everything below 0.5, we predict that as 0. And many of you were asking the question, why 0.5? Right? That's exactly the question today. There's no ground to say 0.5 is a good number. It's just an arbitrary number. Right? Think about earlier the credit card default. There's 3% of the bad guys, 97% of the good ones. And how do you choose a cutoff if you have the probability? That's not easy, right? It definitely depends on your context, your data set, and actually depends on the business itself. I will come back to that later. But suppose there's a cutoff, right? Let's suppose. So this is a big decision. Just keep that in mind. We call that cutoff probability. Suppose there's a number. Let's start with 0.5. If there's a number, then we can compare. Everybody has a probability. We compare that probability with that number. Then we make it 0, 1. Right? Then the remaining will be trivial. The question is really how do we find out the best cutoff, right? So let's continue. Right? Given we have a cutoff, what will be the consequence? So the first thing is we can calculate the misclassification rate. Right? So for everybody, we have a label about good or bad. Then we know this guy is truly has defaulted or not. So we can figure out how many times we were wrong, and that's the so-called misclassification rate. Right? That's typically whenever you do classification, that's the first thing people look at. So what's the misclassification rate? Like earlier we said, if we predict everybody to be good, then we have 97% of the accuracy. Correct, 3% misclassification, right? So that's the misclassification rate. But that doesn't give you the complete picture. Having a 5% misclassification rate doesn't say too much because there are two types of error you can make. So in statistics, we call that type 1 error, type 2 error. There are two types of error. This is a good guy, you say he's bad. This is a bad guy, you say he's good. Two types of error are not symmetric, right? Keep that in mind. Therefore, to have a complete picture, we should have a confusion matrix. Confusion matrix just puts all the cases in the 2x2 matrix. So this is the truly, this is a bad guy going to default, has defaulted or not. Right? That's the true Y. And that's the predicted Y we put on each data point. So if it's truly positive and we predict positive, so that's a true positive. So positive is our prediction. We believe this guy is a bad guy. Positive is a prediction. True or false is our, are we correct or not, right? So this is, we are correct, and he's truly positive. And we predict these guys to be positive, but we were wrong. False positive. So they were actually good people. Then you have true negative and false negative, right? So that are 4 different situations. And we have to separate these 4 different situations because in practice, the consequence may be very different. We just said we can have these 2 types of errors, false positive and false negative. The type of the consequence, the business consequence might be very different. Think about the iPhone Face ID kind of thing, right? Think about you use your face to unlock the phone, right? So there are false positive and false negative, right? The algorithm predicts you are not the owner, refuse to unlock your phone, right? That's false negative, right? You are the owner, but the algorithm label you as negative, so you cannot get in. That's a false negative. That consequence is okay. You just cannot unlock, but try again, right? Wash your face and try again. Right? Let's think about the false positive. Right? Somebody take your phone, the algorithm believes that's a positive. That's the owner, and unlock that. That's a big consequence, I guess. So these two things, we need to make a trade-off. Sometimes you can change the cutoff. Think about the cutoff is really helping you to make a trade-off. When you change your cutoff, you are shifting some of the false negative to some of the false positive, right? And where to stop, where to find the optimal cutoff really depends on the relative cost in your context, right? So we'll talk about this slightly later. But keep in mind they are not symmetric, definitely not symmetric, right? If it's symmetric, then 0.5 probably is okay, right? That's 50-50. But another thing just to highlight, we have been talking about there will be 4 numbers, and they sum up to the total data size, right? We have a data set, we label every data point. Each data point eventually fall into one of the cell. The total is the total data set. And also the numbers in these 4 cells really depends on the cutoff, right? If you change your cutoff, there will be a different number of true positive, a different number of true negative. Things might change, right? And let's do it here. Okay? Let's think about the balance story. There's some x. This is 0, this is 1. There's some good people, bad people. Okay? If I start with a cutoff being, so I have a logistic regression, have a probability. So everybody, I give them a probability. So let's start with a cutoff of 0. Let me use a different. Somehow I cannot change my. Come on. Shoot. Yeah, anyway. So let's think about if we have a very low cutoff. Cutoff is 0. What do we mean by cutoff is 0? We said everybody below cutoff, everybody whose probability is below cutoff is labeled as 0. Above cutoff will be labeled as 1. Right? If we have a cutoff being 0, we label everybody as 1. Right? We label everybody as 1. When we label everybody as 1, these guys will be correct. They are truly 1s. Right? So these are the true positive. We have a lot of true positive, right? And these guys will be wrong. We labeled a lot of positive, but they are not positive. So there's a lot of false positive, right? So a lot of false positive. So when when the cutoff is 0, let's think about the false positive and false negative. So we say we have many false many, very large number in the false positive, because everybody here, they are false positive, right? They're not positive, but I label them as positive. Okay. How many false negative do I have? 0. I didn't label anybody as negative, so I cannot make a mistake in that category, right? I have 0. Let me use the true numbers. So this is 97%. Right? Just in the true data set, there are 97% of the non-default, 3% of the default. Right? So then I gradually go out. C is 0.5. So what's going to happen? Everybody on the left side, their probability, this is their probability, right? Their probability is below the cutoff. I'll label them as 0. Everybody on the right, I'll label them as 1. Okay? And let's look at the zeros. So we call these guys negative. And they are truly negative. I'm okay. But now I started to have one false negative. Right? So I have, this is just made up number. Right? Now I have one false negative. Because I claim this guy is negative, but turns out it's wrong. Right? Then on the other side, I claim everybody on the right side positive. And they are positive, I'm okay. This is a true positive. But how about these guys? Right? I have many these guys. Say, just put some numbers. 20. So think about things when you go all the way to the high up. C goes to 1. Basically labeling everybody as negative. Right? Everybody negative. I don't have issue with this guy, but I'm having issue with those guys. Right? Those are false negative. I claim them to be negative. Right? False negative, 3%. I have 0 positive, false positive. Right? So it gives you a gradual shifting from a lot of false positive to a lot of false negative. And the optimal cutoff is really how much does it cost if you have false positive, or how much does it cost if you have false negative. Right? So that's the idea. And that depends on the business context, depends on the cost on the two things. Right? But there are situations you don't really have a business context. It can be just a data computation. You just predict all these images. Are these the images of cats or not? There's really no cost. I don't know what's the consequence. And there are simpler measures if we don't have the cost information. There's simpler measures. So there's a bunch of all these different crazy measures derived from these 4 numbers. I just list them here. They don't matter too much. But in practice, there are different people use different numbers. Just good to know, right? And just list all the definitions. There's a so-called true positive rate. True positive rate, I have the definition here, right? There's a true positive, this guy, divided by true positive plus false negative. That's this guy, right? You see the ratio? This is among all the bad people, how many you figure out, how many you didn't, right? That's the true positive rate, okay? The true positive rate. And there are several other numbers, sensitivity, recall, different people from different backgrounds that would just use all these different names. Or just appear to be cool. False positive rate is easy, but some people just want to use sensitivity. False positive rate. False positive rate is the other side. False positive divided by the total. So among all the good guys, how many you made a mistake, right? Among all the good people, y being 0, how many mistakes you have. True negative rate, I think is 1 minus. So these two is one pair. Since they share the same denominator, so there's one pair. They sum up to 1. So that's trivial. These two should be one pair, right? Yeah. So there's 1 minus the other guy. There are many others. Precision is given all the positives you have been talking about, how many are true? So that's this one. Right? Among all the positives you labeled, how many are truly positive? Right? And accuracy is 1 minus the misclassification error. Misclassification is the total number of errors divided by total. Accuracy is total number of the correct ones divided by total. Right? That doesn't differentiate the two types of error. No. Then lift is a bit crazy. What's that? Try to read that. I'm going to skip that. The key, I think that the real important one among these measures are the cost. The cost we have described. It really depends on your business context, depends on what the cost of having one case of false positive and what's the cost of having one case of false negative. Right? They may not be highly symmetric. And also, we don't really need the exact dollar amount for these two things. All that we need are the ratios. We need the ratio so that we can trade off these two type of cost. So we can find the optimal one. Right? So very often when we talk to business people, we just say, yeah, I probably my algorithm make this two kind of mistake. What do you see the consequence? Like, what's the ratio of the two things? Right? They may not give you a solid number, but think about how uncomfortable you will be if you have a false negative relative to a false positive. Right? And just again, since these four fundamental numbers are determined by the cutoff, all these measures as derivative of these four numbers are functions of the cutoff. If we change the cutoff, all these measures will be different. Right? Especially the key thing, cost and the misclassification rate. These are the common things people are using. All right. So next, let me do some plots, and we talk about how do we find the optimal cutoff. So later you will see in R, there's a beautiful package automatically plot all these things for you. Right? It just say the task is, I know all these numbers depend on my cutoff, so why not just let the computer try all the possible cutoffs from 0 to 1 and plot all these numbers for me. So you can see the trade-off. Right? You can see how to choose your cutoff. So there's a beautiful set of tools. This is one example applied to the default data. So this is automatic, 2 lines of code. You will see a picture of 3 lines, including the plot. You will see this thing. So it basically tried the cutoff. So this is the cutoff. Right? From 0 to 1. It tried many values. For each cutoff values, it calculates the corresponding number of true positive and false positive, all these things. Then convert those things to error rate. That's the misclassification rate, false positive rate, false negative rate, whatever you like. Yeah? There's a big collection of measures you can choose, right? Automatic. Let's see that's basically the table I was trying to enumerate. When we start with a cutoff 0, we'll have a 97% false positive rate and 0 false negative rate. As we increase our cutoff, false negative rate goes up, and false positive rate goes down. Right? One goes to 0, the other goes to the other things. Something like that. And the error rate is somewhat the total of that. And the interesting thing is, in general, the error rate should be a U-shaped. As you change your cutoff from 0 to 1, the error rate should be a U-shaped. But this is not a U-shaped error rate. It's actually going up a little bit, but not that much. But this is really because that the data is unbalanced. You only have 3% of the default case, and towards the end, logistic regression may not find a good solution better than this 3% error. So that's the minimum kind of thing. Yeah. So I'll give you the code, and you can check the details of the data, why and what exactly is the value here. Are they increasing slightly here or not? Right? You can check all these things. But here is just a plot. Yeah. So you can plot all these things against all these things. There are all these measures. So this is plot the accuracy. So we just said accuracy is 1 minus the error rate. So that's flip the earlier black line. So that's nothing new. You can plot the precision. And remember, we have a definition for precision. That thing kind of goes crazy. Huh? So you can see all these things. And the ultimate thing is this guy. This is the situation when you don't have a business context. You cannot specify the cost. If I cannot specify the cost, how do I choose the best cutoff? Right? That's a no. This is even more than that. This is in a situation like I don't want to choose a cutoff at this moment. I just want to choose a model that gives me the overall better performance relative to other models when for average cutoff. So on average, when my cutoff is changing, my error is changing. But on average, how much is the error? So that's the idea. Let me show you the picture. This is a famous ROC curve. So whenever you don't have a business context, this is the gold standard for choosing the best classification method. There's a complete name for that. I don't understand what the context of that. It's some like electrical engineering terminologies. But this is the so-called ROC curve. So ROC curve actually plots this guy, false positive rate, against the true positive rate. So it shows you a trade-off. It's still a line. It's still a line generated by choosing different cutoffs from 0 to 1. For each cutoff, you have a corresponding false positive. You have a corresponding false negative, true positive, and just put the point there. And you just connect everything together. The beauty of this thing is it shows you the trade-off. The trade-off of like, I start from here. I may not start. This might correspond to a cutoff of, what's that, 0, 0. Let's forget. Where am I? So if my cutoff is 0, my false negative is 0. I think I don't have false. I have a false positive. So this should be cutoff 1. I have a 0 false positive. Go back. 0 positive. This is cutoff being 1. Then this would be cutoff being 0. Right? You just move along that line. So think about moving changing a little bit of the cutoff. Let's reducing the cutoff a little bit. What you're gonna sacrifice is you're moving up along this line. You're moving up to here, for example. That says you are going to sacrifice a little bit in your false positive rate, right? Horizontally, you're moving a little bit. But your gain on your true positive rate is huge, right? It tells you the trade-off. When you shift your cutoff downwards, you are going to change both of these measures. But the true positive is a good one. False positive is a bad one, right? By sacrificing a little bit bad ones, you're going to gain a lot in the good ones. And but towards the end, you need to sacrifice a lot of the false positive rate in order to get some little change increase in the true positive rate. Right? So that shows you some gradual trade-off over time when you move your cutoff from 1 to 0. Right? But what's kind of how people use this is basically people look at this black line, and this black line actually the higher the better. The higher the better in the sense that given the same false positive rate, a higher line will give me a higher true positive rate. Right? At the same level of false positive, I'm going to have a better true positive. Right? The higher the better. Right? So the most ideal case would be a square. That's the most ideal case. Right? You want this to go up. Right? So basically, in order to compare different curves, sometimes it's not easily comparable because you might have one logistic regression model. That's today's homework. You plot this thing, you will see that. And you might have another logistic regression model that looks like this. So it's very hard to compare these two because sometimes this is higher, sometimes that one is higher. How do you compare? So for the sake of ease of a comparison, people introduce this idea called area under the ROC. So you just take an integration over this curve, measure the whole area. And you know that the total area is at most 1. Right? So that gives you a measure like R squared kind of thing. The closer to 1, the better your model is. So for any curve, you can always calculate that area. So that's AUC. And you can see this is different from earlier. Earlier, we fixed at 1 point. We say we identify the optimal cutoff. That's here. At this cutoff, I have this much of false positive. I have that much of true positive. That's my optimal. I stay there. Based on my context, I choose the 1 point. This guy is really, I refuse to choose a point. All these points are possible. And I would determine when to choose my point later. But I want to find a model that is in an aggregate level better than the other model, right? By choosing the area, right? So that's the kind of idea. When you really don't have a way to decide the cost or decide the trade-off, so that's a standard. Yeah. But it's not. If you have a good cost estimate, that should be important, right? Because sometimes this is better, sometimes this is better, depending on what's your cutoff, right? If you have a clear understanding about the cutoff, you shouldn't use that. But very often, in most of the kind of a data competition, they don't have a definition of the cost. They just do this way. All right. Now, let's do this first. So we are done with the classification part of two. Yeah.
Why not we just find the slope of this curve when it is equals to, let's say, when it's 45 degrees? That's the point where your increase in positive rate is equals to your increase in false positive rate. So that's
if you believe that the cost is roughly 1-to-1, then 45 degrees is the optimal. If you believe the cost ratio is 10-to-1, probably you should choose a different slope. It's really, that slope is really determined by your two types of cost. And yeah, that's basically the same idea. If you tell me the cost, later I will show you in the code. There's an easy way to plot how the cost change with respect to cutoff. And there should be an optimal cutoff out there, right? That's the same idea. Yeah. Okay. So that's about classification, going from probability to the labels of good guys and bad guys. That's not trivial, right? Not trivial. And then we move on to the last topic. That's the generalized linear models. So we have seen the linear regression and logistic regression. We have seen the correspondence, right? There are a lot of things are in common, but there's some slight difference. So what are the things in common? We all have a bunch of features. We combine the features using a linear formula, right? The same thing here. The difference is in linear regression, we just jumped directly to the end. Our prediction will be this number, right? But let's slow down a little bit. Think about what we have been doing. We have been saying this is the mean of our y in linear regression. So basically what we're trying to say is on average, our y should be around this eta. And that's our prediction at the same time for our y, right? Because this is normal. The mean, the internal connection we have trying to build is that the mean of our y we're interested in predicting will be equal to the combination of the predictors, right? And today in logistic regression, we have been doing pretty much the same thing. We have the credit score, and we said the credit score is not in the right range, so we use the logistic function to convert the credit score into the range of 0 to 1. And we use that as the probability of default, right? But if you think again, you can see actually the probability here is essentially the mean of our y. Because the y is a 0, 1 variable. The mean of a 0, 1 variable is the probability of being 1. Right? Do we see that? Ey is y can take value 1 times the probability y equal to 1 plus y can take value 0 times probability y being 0. Right? The second term is gone, so that's a probability of. Right? So the probability is just the expectation. So in that sense, we can nicely unify the whole framework. In linear regression, we are using this thing. We are basically predicting the mean of our y. In logistic regression, we are also predicting the mean of our y. We're doing the same thing. Right? The only thing that differentiate the two would be the distributions. Here we have a Gaussian normal distribution. Here we have a Bernoulli distribution. That's the only difference. Right? And that's because our y takes a different value. Right? So inspired by that thing, we can include many other way of doing things. Like before that, let me talk about the link first, because what's special here is we introduce the logistic function as the transformation, and also we mentioned all that we need is a mapping from minus infinity to do 0, 1. Yeah? It can be anything. This is just one of the solutions. Yeah? That's the logistic function is one of the solutions. So in practice, there are many other solutions. There's a probit transformation. There's also a tobit transformation. Right? They somehow come up with all the names like they're from the same family. There's a logit. There's a probit. There's also a tobit. You can check Wikipedia. But all these are different mapping from that infinite range to 0, 1 range. So we have seen the logistic function. We have done that it's S-shaped. But the probit idea is really, I can find many S-shaped functions here. Any probability distribution, the cumulative one, cumulative probability distribution will give you sort of a S-shaped function. You can put anything here. So for the sake of simplicity, we just put a normal distribution here, right? So this is the cumulative distribution function of normal. Okay? It's just normal. Okay? Normal distribution gives you normal distribution itself plots like a bell curve, right? That's a PDF. But if you take the integration, that's going to look like this, S-shaped, right? So it doesn't add much, but I just say this is not the only choice. There are many other choices. If you like, you can just replace that. Right? And how do we choose? We would use AIC to see would logit fit our data better or probit fit our data better, right? If you want, you can do such a comparison. This is the typo. This is logit. Logit versus probit link. So you can do, earlier we have been doing this using logistic regression. We have the binomial family and we have been using the logit link. If you want, you can just replace that with probit. It doesn't change too much. You'll get a different set of solutions. The meaning of the betas will be a little bit different. Hopefully we still have the same sign, but roughly, not very the same. But what you can choose is you can look at the AIC. AIC is a measure of the goodness, badness of fit. So logit seems like smaller. It's a better fit. That's it, right? If you're not comfortable with choosing the default link, you can try different links and choose the better one. But that's not the main point. The main point is really on top of the link you can play with, the mapping, you can also play with the family. Right? So we have been talking about all these different type of Y. We have the Gaussian, the linear regression. We have the logistic classification type of Y. Either is a 0, 1, that's a Bernoulli, or is a count, like the Titanic story is a count binomial. How many people survived out of 10 passengers? And we also have other counting process, like counting the number of goals. The exponential, this is the time until an event happens. So we have all these different type of Ys. So follow the same line of thought. We can just try to introduce all these different mappings. Right? We have logistic regression, logistic function as the mapping. If you like, you can replace that logistic function with the appropriate thing. You can also do the mapping, so that belongs to the Bernoulli family. And in Poisson, we can use the exponential as the mapping. Okay? Think about there's nothing magic. All that we need here is some sort of S-shaped thing, right? 0 to 1. All that we need is that. So we have two choices here. And in the Poisson story, the Y we observe is how many goals in a football match. Right? They are integers. This is ugly. But just like here, we are not really using the regression tool to predict the 0, 1s. We're predicting the probabilities. We're predicting the means. The mean of the number of goals can be anything, as long as it's positive. So all that we need here is, so here we need 0 to 1. Here, all that we need is some 0 to infinity. Okay? That's all we need. If we have a mapping from the sort of features to 0 to infinity, we can use that as the mean of our number of goals, then we are done. Right? And turns out this is the what? Turns out this is what we do. What's the mapping? This is the exponential function, and that's the mapping. Your eta can be anything, but the output is going from 0 to infinity. That's it. Right? That's the whole. There's nothing special. We just try to find another mapping. And exponential, we have a similar thing. So let me not explain that. This is something like that. But it's just about. I just want the right range. As long as things are in the right range, I can manipulate the parameters and find the best fit. Okay, so the technical details are not important. If you understand how to run logistic regression, running Poisson regression is just changing that family. Right? The important thing is really at the starting point of analyzing some data, making some models, we do need to check what are the Ys we're working with. Are we working with categorical Ys, or are we working with accounting Ys? Right? Last year we had a midterm exam. I'll show you the exam from last year. Was predicting the number of Pokemon showing up in some area of Singapore. Right? So there I have some data on that. And that the most important thing to identify is that should be a Poisson regression. We're counting how many Pokemon showing up in a period of time. It's not a linear regression. Right? That's many people didn't take note of that. Right? So for us, really is we need to choose the right family. That's it. Right? All the other things are the same thing. So let me show you an example. This is a Poisson regression. When we use that, we use that for count data. Count data is discrete and somewhat skewed. That's not important. Non-negative. Linear regression will not work because of all these things. We just said we introduced the link, right? Just to make the correspondence. Logistic, we go from X to P to the class. And Poisson, we go from x. We are using x to, this is logistic map. This is exponential mapping. We use the x to figure out the mean. Right? So I use a lambda here, the same thing. Right? Having x, I can use x to predict the mean. This is also the mean. This is also the mean. I'm predicting the average number of goals in a football game, and that's my prediction. I don't need a classification. That's done. So the best prediction is the mean, right? If I'm predicting the number of goals, that's the best prediction. So that's the same thing here. I don't need to have the second step of converting probability to class. So that's the best I can do, right? So let me show you how to do that. So I have a small data set about football games, 150 matches from English Premium League. And the data looks like this. I'm splitting each game into 4 different groups. This is a game ID. So the first 4 rows is about the same game. But I'm counting how many goals in the first half by the home team, first half by the away team, second half by the home team, second half by the away team. I'm counting the goals in these 4 groups, right, for each match. So I have 150 matches. So for each match, I have 4 different data points. So in total, I think there are 600 data points. 600 data points. That's the overview of the data. Right? You can see there's a mean that on average there are 0.6 goals. What's the meaning of that? On average, 0.6. We are taking the mean of this column, right? On average, it is 0.6. So it says there are 0.6 goals in each half by one of the team, right? On average, that's stuff. Right? Keep in mind, I'm chopping the one game into 4 chunks. So what I'm trying to do is I want to understand the number of goals. What's the dependency of the number of goals on home team, away team, on first half, second half, right? That's my features. So I'm running a Poisson regression, right? That's the only difference relative to the logistic regression. As long as you have your model correct, my y is the number of goals, the goal column. So I have x1, x2, half and whole. All right? Everything else is the same if you compare that with the logistic regression report. Okay, that's the beauty of the generalized linear models. All these deviance and all these error measures are unified. They mean the same thing. The badness of fit, everything is there. Okay, so let's see how do we understand this result. So we run a Poisson regression. Y is the number of goals. So we're using this first half, second half, home team, away team to predict the number of goals. So we have such a result. First thing, home team, away team is not significant. Huh? Same way of interpreting things. What can we conclude? Yeah? There's no difference between home team and away team. Right? So how about the second half? Second half, positive and significant. What do we say? We should expect more goals in the second half. Right? But how much more is not that clear. This is not linear. If it is linear, this is the difference. But this is not linear. Right? Then we have the quality of the errors, AIC, all these things. Right? Okay. They're all the same. So if I really want to understand the difference between second half and the first half, I need to go back to my model. What? Yeah.
The AIC is higher than the null deviance.
Yeah.
Does it mean that the model does not really explain much?
No. Here in the Poisson model, the definition is slightly different. So you cannot compare the magnitude here with the magnitude there. The only thing you can compare is, given the same data set, I may have different variables in my model, I get 2 different AIC. I can compare that. Different model on the same data set, but not across data sets.
But here the non-variance
That formula, I don't think that's the same thing. That formula doesn't apply. That's a good point. I think there's 2 times of the residual deviance plus 6, right? Yeah, let me go back and check why this. I guess earlier the question is we just say this 2 has some relationship from their definition, but this doesn't apply here, right? There's something missing. Let me go back and check that.
And we can't compare, if we have used the same data set and we use different families.
Yeah, you can compare.
Can you compare the
Yeah. It applies the same data. Whatever model you build on the same data, as it measures how your model represents your data. So you can compare. Yeah. Okay. So I really want to understand what do we mean by having a difference here, right? So we need to go back to the model. What do we say about the model? So yeah, I want to understand this coefficient, right? This beta. So what was the model here? Our model is the expected number of goals is exp beta 0 plus beta 1 for away. That's not significant anyway. Beta 2 times second half. Right? That's our model. We have some betas. So if we know this is not significant, we remove that. Right? That's just ignore that. So what can we say? So having the rest, we only have the first half and the second half. If it's the first half, then we don't have this dummy. The resulted prediction is only the exponential value, exponential function of a beta 0, right? When it's in the second half, then we need to add this guy back to the formula. That's it, right? So the question I want to answer is, at the end, how different is the second half versus the first half, right? But what we have is, on average, what we should expect in the first half, what we should expect in the second half, right? So the difference is just take the ratio of the 2. What do you get? You get the beta 0 canceled out. You get this thing, right? So that's my beta 2 here. So what do we say? We say that's 39% more goals. So that's a ratio, right? So in the second half, we have, on average, 39% more goals than the first half. Okay? So going back to the model, we can now explain the impact of being second half is really this guy, but in a relative sense, right? It's a relative sense. Okay? So that's what I meant, that the important things is to understand when you run a Poisson regression, the underlying assumption is this is what you're doing. That's important. Right? Then being able to interpret the betas, that's important. Right? That's so far. Okay, the other for away is not significant, so we can take them out. Right? There's no difference. We have seen the AIC. That's again the only standard for model selection for now. For Poisson regression, this slight extra check we need to do is if the Poisson assumption is satisfied, you should have the residual deviance and the degree of freedom roughly the same. So there's something we should check after running this. So it says this guy should be roughly the same as this guy. Right? That's fine for this one. So you can say, yeah, in football matches, the number of goals roughly follows Poisson distribution. This is a good model to be applied here. In practice, it may not always hold. If it doesn't hold, typically the deviance is larger than the degree of freedom, it says Poisson is not a good assumption. You need some more crazy version of that for the counting process. You need some other families. So there's a quasi Poisson version and there's some negative binomial. So you need to have some more flexible family to measure that, to represent your y. That's just a quick thing. Survival analysis, let me just skip that. It's not so important. It's about y is about time until something happens. So there's to measure some time, right? And we use an exponential distribution to model the time until something. This itself is a big area. In R, there's a super big package called survival, capturing all different kind of contexts. So whenever you have some y being like that, so you need to go to the survival package. There are a lot of tiny details. Let's not get there. But just keep in mind, generalized linear model can capture that kind of context. Right? All right. Coding time. How many of you have gone through the code I uploaded last time, linear regression? You're the only one? Last week I uploaded a code on linear regression. Last time we didn't have time to go through the code, but I put the code online. Yeah, in the afternoon I was doing this and they were complaining this is too fast. But it was basically repeating the linear regression thing, just changing the family. So if you haven't looked at that one, this is going to be a bit challenging, but just stop me whenever you have a question, right? I assume you have looked at that, so I tend to run very fast. Because it's just changing the LM with GLM. Okay? So we'll start. These are my keyboard. We'll start with a credit card data set. The credit card data set is in the package ISLR. ISLR is the package in the of the textbook. Right? Inside the package, you have many data sets. The default is one of them, just for the sake of illustration. So you can check the data set documentation by using a question mark. It shows you the documentation about some description about what's going on. There are 10,000 observations. What's the meaning of default? All these things. Right? This is a simple data set. There's not much we need to worry about. So head is for checking, quick check of the structure of the data. Are there anything we need to fix? This is showing the first, 6 rows? I remember it was 5. Oh, how come? How come this was 6 rows? So we have been talking about the structure, right? We don't need to spend time on that. Then we can do a summary. This is a quick visual exploration. The highlight thing is here. We just said there are 10,000 data points, but there are 333 default cases. Right? This is not really balanced. When we talk about balance, it's about the y, right? But sometimes x also needs to be balanced, right? If you only have 2 students in this whole data set, then there's not much you can talk about students. But the issue is really this guy, right? So I'm doing a strange thing here. I think it's just for the sake of illustration. Actually, you can just directly run logistic regression, use this as the y, and use the other as x. But here there's a no and yes. And this is a factor. So factor are ordered alphabetically. No will be the reference. Yes will be the case to be predicted. So that's okay. Now we don't need to change something. But some other time, for example, you have true and false. Not true and false. Some other time, your coding will be different. Just be careful what are the things you are predicting. Here, you're predicting the probability of yes, because that's the second level in your factor. I think, yeah, in one of the exam in the past, many people messed up the ordering. Don't remember which one. If you're not comfortable with this, I think the safe way is construct a variable on your own, code it that into 0, 1. You know you're already predicting the probability of 1s, right? So I guess that's why I'm doing here. And also later, in some other classification package, it doesn't take the factor y directly. It expects a 0, 1 coding. So you would need to do this manual conversion. So this is what I'm trying to do, manual conversion as numeric. So internally, this is a factor, right? Factor, there are 2 levels. So internally, no will be level number 1. Yes will be level number 2. So if you convert this whole guy into numeric, you will get a bunch of 1s and 2s, right? 1 means no, 2 means yes. And that's not what we want. We want a 0, 1. So I do like -1 here. And that's the y I'm using here. That will be 0 and 1. Okay? Later in the gradient boosting machine, you will need to do this many times. So I just put it here. This is the, most of the things are already in the slides. This is when we run it as a linear regression. We just say, yeah, anyway, that's 0, 1. Oh, that's why I do that, make it 0, 1. I need to run this as a linear regression, so convert that to 0, 1. You can run that linear regression, but there's not a point. You can do the visualization. So that's the plot in the slides. Yeah? I think that's not a... Are there questions on how to run linear regression? All right. In linear models, you just need to specify data and your model. Right? Model is what is your y, what is your x. Okay? That's it. So logistic regression, you need a GLM. GLM, we mentioned again the model, that's the formula, the data, and the family. We said we are doing logistic, so it's binomial. The logit link is default, so you don't have to do anything. Just leave that empty. And I'm saving the output in the object called GLM1. Let's do a summary. That's what you have seen on one of the slides, I think, as the first model we built. That's the summary of the model. One thing I want to show you is in this model we have built, there are a lot of things. STR is the standard one to inspect, standard function to inspect an object. So the object is huge, actually, GLM1. There's so many different things. In some situation, you will need to have to pull out the things from this object. Like you want to know what's the AIC of my model. Yeah, where do I find AIC of this model? Let me see. Here. Right? You can find this is AIC. So in case I need AIC, I can just do GLM1 $AIC. That's the number, right? So you need to learn how to find all the data hidden here. There's so many things. Just try to navigate through this guy. And then I'm doing the plot. So this is again the picture on the slides, overlaying the logistic regression fit on the true data. And you can see the fitted value is digged out from the GLM1 object. There's a bunch of fitted value. So that's in the training data set, you have 10,000 data points. So this is 10,000 probability we got from the logistic model. And the balance is the x, doesn't matter. Also, we can do prediction. like earlier on the slides, we have been using the model and using the beta to calculate all these formulas. But in the coding part, we don't need to do that manually. So there's a predict function. Predict can take out a trained model, GLM1. This is what we have. Let's say, give me some new data points. I will do the prediction using the model. The new data point, the new data is supposed to be a data frame, and you need to supply all the required x. So in our model, x is just balance. So you need to have a data frame with a column called balance, and that column has two numbers. Right? I'm just constructing a new data set on the go. Right? This is one data frame with one column called balance with two rows, 1,000, 2,000. So this is to answer the question in the slides. What if I have two new customers? One guy has a balance 1,000, the other guy has a balance 2,000. What's their default probability? The important part here that wasn't there in linear regression is this guy, type equal to response. This is one of the ugly part of R. You can see all the previous part is pretty much just like in linear regression. Right? There's not much changes. Later, when we do trees, when we do random forest, when we do boosting, they're all pretty much the same. But when it comes to prediction, they all use the same function, predict, but the type, the definition for types are all mixed up. Here, type being equal to response means I want the probability. Later, you will see type equal to response give you something else. And if you want the probability, you need to say type equal to probability. Right? So you need to be able to find the documentation. When I'm predicting something, I want the probability instead of the yes or no, instead of the credit score. So you can get all these things if you want. The different type, you can just get a credit score also. So you need to be able to find the documentation. But I'm running this predict function, and this predictive function applies to a linear regression model, generalized linear model, random forest in the future. They're all called predict. But the predictor is actually an umbrella of many sub-functions. That's the beauty of R. So that's an umbrella predict function. It takes an object in its first argument, and it's really try to identify what's that object. Oh, that's a GLM object. So I'm going down. I have an umbrella. I have many small predict functions. I'm going to pick out the corresponding predict function that is supposed to be used on a GLM object. I'm using that to run the prediction. Right? That's try to make the code really consistent. But the issue is when you need to check the documentation, you don't see anything. You just have predict. Predict is a umbrella kind of function. It doesn't tell you how to do prediction. It doesn't have anything. Right? So here, what's the real predictor, the member function is predict.glm. So you can type predict dot. You will see there's a predict.glm, there's predict.lm, whatever predict, there's the umbrella function. And if you load a library like a tree, I don't have a tree. Yeah, I upgraded my R. Shoot. Whatever. Later you will have many predict, right? But the real thing you need to see is this predict. So you can check the documentation here. The worst thing about R is whenever you upgrade the R version, you have to reinstall all the packages. So this is predict.glm, right? That .glm part is automatic. You just figure out what object you're doing and pull out the corresponding predict function. And all the other things are the same. Whenever you're predicting, you need a trained model. You need some new data. That's standard. But the real thing is the type. And for this guy, you have three choices. We have been using response. So you need to be able to read the documentation and figure out what they mean. Link should be the credit score. That's the adder thing. Right? It doesn't map that to the 0, 1 You can get the link, you can get the response, and you can get the terms. What are the terms? I don't know. So you can try to run all this. Later you will see in other predict, you have all these different kind of types. It's quite confusing, right? So be ready to check the documentation. But let me just do the prediction. So what are the predictions? So I have the two new data points and balance 1,000, 2,000. I have two probabilities. I think that's also the probability on the slide, right? That's how we get that. Okay? Are we good? Then next, GLM. GLM2, I'm doing default with respect to students. There's nothing new. That's the report on the slide. I don't think there's anything new. And what I'm doing here, plot the student versus the fitted values. So that's what. So students can only be yes or no, right? The fitted value is the predicted default probability for non-student and for students. That's also the two numbers we have seen on the slides, students and non-students. 4% and 2%, something like that. Right? So that number actually comes in the fitted value. So you can just paste that guy here. So for students, you get one number. For non-students, you get another number. Right? That's 10,000 of them. Third model, that's the massive model. I just use all the features. And yeah, there's nothing to add. Are we okay? That's the logistic regression. Important functions, just GLM and predict. That's build the model and predict on a new data set. Right? This is, again, different from the k-nearest neighbor, which combines the two functions in one. This guy is separate. How do I build a model with the training data, and how do I predict outside? And last time, some of you were very worried about the model selection. We have so many features, and how do we choose all these interactions and nonlinear thing? And actually, I have a magic function last time in that code, but I guess none of you have read that. So this is a so-called step AIC function in the math package. It does the automatic model selection for you, forward or backward or both ways. We have introduced those ways, right? Just include a variable or remove one variable automatically. But last time we said we were using R-square or some other measures, significance to move. This guy used AIC because in all the GLM models, AIC is the common standard. So you can always use AIC to do model selection. So let me run. So what you need is you need to specify a starting model. Let's start from somewhere. You need to have a trained model. I used the GLM3 from above. So that's a starting model. I'm using step AIC to adjust that model. Direction is both. You can add things or you can remove things. Okay? So you can change the orders. This is an easy situation, so it just repeats just two iterations. So this is model GLM3. I have all the features in. So what is step AIC doing? Step AIC sees my model, and it realized I can make 4 different changes. I can remove the income variable. I can do nothing. I can remove students. I can remove balance. Are we okay? So this is a complete model, and I don't have extra features. So that's already full. I can either remove one of the 3 or stay the same. So what step AIC would do is it just try all these 4 models and figure out its AIC and see which one is the best. Turns out remove income gives us the smallest AIC. So that's the direction to go. So you just try this thing again. The next model is default with only balance and students. So that's the starting model of the second iteration. Now it has, again, 4 different things. You can stay the same, add income back. That's not very smart. Minus students or minus balance. Right? You compare all the 4 combination possibilities. Stay the same is the best. Then we stop. No more changes. Right? There's no more changes can improve your AIC. This is a small model. If you start with a massive model with all the interactions, let's try that. Let me make GLM3 much bigger by adding the interactions everywhere. Does that work? Of course. This is not many, but still fine. Let's do a step AIC. It takes some time. So it just travels all the way, not many. It travels all the way from the starting model, minus one of the interactions, minus another interactions, minus another interactions, minus another interactions. At the end, still the same model. No need to add any interactions. But that's a comforting message, right? Well, at least we tried all the interactions and none of them helped. So that's still the same model. Yeah? So that's, in the old world, that's the best thing you can do. Right? Okay? And the output is the final model. So you can save that. I'm saving that as GLM best. So that's the best according to the step AIC. I can see a summary. So that's my best model with only these two variables. Okay. The other thing I think I have that in last week's code also is the update function. So sometimes you really just say, I have this model, but I hate this thing. I want to take it out. You don't need to build everything again. You can say, I want to update my model. I don't want to change my y, so I use the dot. Everything stays. I don't want to change my x. Everything stays, but I just want to minus this income. This is a quick way to take out one variable if you're doing. What's going to be there? That's the crazy interaction model. Yeah, anyway, you get the point. And this is the same set of functions for linear regression, for logistic regression. In case you want to pull out all the coefficients. What? So many? I need to go back. Let me go back. All right, if you need to pull out the coefficients, there's a coef function showing you the beta 0, beta 1, beta 2. Right? If you need a confidence interval, it takes some time to calculate, but there's confidence interval for your betas. Fitted value, so those are the 10,000 fitted value. If you want the probability or you want other things. Residues, so that's a deviance for each of the data points. And there's some crazy plots that's important for linear regression, but not important for logistic regression. Let's just ignore that. Okay, so that's logistic regression. We have introduced how to do that and how to do a step AIC to do an automatic model selection. Okay. Next, this is the more beautiful guy is how to replot all this cutoff thing. Right? When we change different cutoffs. What are we doing here? Let me take the history. So the first thing is we said this is the second step. The first step, we have the logistic regression, the best model generating probabilities for each data point. Next step is moving from probabilities to the labels, good guys, bad guys. So we need to first get the probabilities. So I guess I get the probability from the GLM4 model. That's the best model we got. So we predict again. Without supplying new data, it predicts use the training data. We need the probability so that type is response. So I'm plotting the histogram of that probability, a lot of zeros. but a bunch of high numbers, right? That's just a probability. And you can make a naive prediction. So that's a GMM4 prediction. It's a naive one if the probability is larger than 0.5. Let's do it true, otherwise false. And based on that naive prediction, we can calculate the confusion matrix by using the table function. Okay? Table just count all the combinations, as I show you. What the table function does is, if you have two categorical variables, it just do all the permutations and all the combinations and count how many fall in each group. Right? That's exactly the false positive, false negative thing we want. And yes or no are coming from the true Y from the data sets. True and false are our prediction generated here. GRM4 prediction, true and false. Right? So that's the confusion matrix, but not in the right order, I guess. No is here. Yeah, these are factors, so this is alphabetical. But that's what we have. Then we can calculate the true positive, true negative. We can pull out those numbers from that matrix and calculate all these crazy measures. Okay? That's for a given cutoff. You can do that manually. Right? Now let's do try all the cutoffs. There's a magic package called ROCR. It's a package to plot the ROC curve in R. That's why it's called ROCR. But it's so magic that it's a nice designed package. So let me try to explain. So there are two parts. The first part of this function is called prediction. It's not predicting anything. It's different from the predict function. It's a prediction. Prediction is to construct an object with two columns of data, the true Y's of each point, the true Y's, and the probability you have been predicting on these things. Right? So that's the output from the logistic regression. You should have the true Y's. You should have the probability prediction. So what this guy would do later is, by changing the cutoff, then compare the probability with the cutoff, you will have the Y predictions. Then you compare the Y predictions with the true Y's. Right? How many false positive, how many negative. But this is just first step. It constructs a prediction object by combining your probability prediction and the true Y's. Right? And this step doesn't do anything. Oh, it actually does a lot of things internally. Let's see what's inside. So that's the GLM4.pred. This is an prediction object. But inside, it has done a lot of things. The important thing to note is, I'm just giving this guy the probability and the true Y's. Internally, it already done a lot of things, like it already come up with 9,504 different cutoff values. You see the cutoff? There's a bunch of cutoffs it will try. It just automatically come up with this bunch of cutoffs. Starts from infinity, that's strange, but yeah, there's starts from very high numbers all the way to 0. Right? And also based on each of these cutoffs, we said once you give me a cutoff, I can calculate the false positive, false negative. Right? So it already did the things. False positive, true positive, true negative, false negative. Each of them is a long list of 9,504. I don't know why 9,500. I have no idea. But for each given cutoff, there's a corresponding set of false positive, true negative, false negative. Okay? So that's, it already did all the things. The fundamental 4 numbers in the confusion matrix, it already did. The next thing is really, you tell him to plot the cost or whatever. So the fundamental data are already in there. So that's the first step, having the prediction. And the second step is to calculate the performance measures by using the performance function in our CR package. performance function just says, give me all the true positive, false positive numbers, and tell me what are the things you want to calculate. Okay? For example, I'm doing false positive rate. False positive rate as a function of the cutoff. Right? So let me run that. Let's see what's the outcome. I'm saving that here, and let me see what's inside. What's inside here is I'm plotting false positive rate. X is my cutoff by default. If you don't specify X, that's going to be the cutoff. Y will be the false positive rate because you said that. So this is a pretty shorthand name. It's in the documentation later. I'll show you. These are the X values. Basically, they are the cutoffs. They are the Y values. They're the false positive rate. Right? So that's all the numbers. It doesn't do the plot. That's a second step. So if you want to plot, you can just do it here. Just plot that guy. So that's the 9,500 values. Okay? This is a cutoff. This is false positive. Okay? So let me show you the documentation of performance. Performance is the second step. It first takes in a prediction object we just constructed, and you need to specify what are the measures you are interested in, because there are just too many. There's a list of measures. They're here, and their names. ACC for accuracy, ERR for the error rate, misclassification rate, false positive rate, for out, same as false positive rate, all these things. So all the things I have been putting there is somewhere. Okay? You can plot anything. AUC, everything is here. So let me replicate the pictures in the slides. I have a false positive rate, I have a false negative rate, and I have a total error rate. Right? So we just have the three things. Then we can just plot them on the same picture. So that's the thing in the slides. Okay? So we didn't do anything manually. We just say, plot this thing for me. Right? You just choose the measures you like. I'll have some legend. Doesn't matter. So I have these also on the slides, the accuracy, right? Remember, I have this ugly precision plot. So you just say, I want precision now. Show me the numbers of precision. And yeah, you basically can choose any measures. Measures will show up on the y-axis. X-axis will be the cutoff, right? Alternatively, you can actually also change your x-axis. Some of the time you don't want to plot along cutoff. So this is the ROC curve. What? Oh, here. So this is the ROC curve in the slides. We just said in the ROC curve, on the x-axis is the false positive rate, and on the other side is true positive rate, by definition. So you have to plot these two correspondingly. So this is the way to do that. Earlier we just specify one measure that's going to show up on the y-axis. You can also change the x measure using false positive rate. Okay? That's false positive rate. Okay? So that's going to give you the ROC curve. Add a diagonal line just for fun. Yeah, earlier I forgot to say. So the useless model will be a diagonal line. The worst case is every 0.1 increase in false positive rate is accompanied by 0.1 increase in the false negative rate. You never separate the two anyway. So it's the worst. Useless model. Also, you can do AUC, but just keep in mind AUC is not related to the cutoff, right? It's the overall area. We just talk about that. So it's performance AUC. You will get that, but the output is a bit ugly. You can see what's inside the AUC thing. It doesn't have an X. all the other things we plot have an x being the cutoff. It doesn't have an x because here we don't have an x. Y is the AUC curve, and the y value is sitting here, just one number. Right? It's not a series of numbers you can plot. It's just one number. And pulling out that number is not easy, so I just put it here. So I need to go to that object, use an @ sign to pull out. This is an internal object. Right? Pull out the y values here, y values. Y values itself is a list. This double bracket is a list, right? We're pulling out the first element in that list, that's this number. Right? So that's the number. So you can dig out that number hidden inside the object. Right? But it's a bit takes some time to find out. Okay. So then we have all the other plots. They're not so important. It just typically people like to draw those things. The final thing I want to highlight is the cost plot. So we didn't put that in the slides, but you can actually plot the cost. So when you plot the cost, the measure is cost, but you need to specify what's your cost of false positive, what's the cost of false negative. The absolute magnitude is not important, but the ratio is important. Right? The ratio of the two is important. I just put 1 to 10, just for illustration. Now you can plot. So that's how your cost will change with respect to your cutoff. So you can see that's my optimal cutoff should be somewhere here. Gives you the minimum cost. Right? So that's the situation. And then you need to see how. I can eyeball this curve and find the optimal cutoff about 0.05. But how do I get this number? You need to see inside. Inside, it's a line, but inside basically a series of x values and a series of y values, right? So you need to find the minimum. Where do I find the minimum of the y values? So this is a which min. So which element minimize the y values? It tells you the 871, 17. Then you need to find the corresponding x values. Are we okay with that? So the first line, find the minimum y value. So that's this number, the minimum y. The next one, find the corresponding x value. There's 2 lines of code. It's a bit dirty, but that's what you can do. All right, I'm done. The probit I don't need to talk about this one. So I show you this on the slide. Okay? Okay? Good. Have the Titanic data. Probably I'm not going to talk about this here, but do go through the Titanic code because the homework is pretty much the same thing. Yeah. Okay, I guess we have to stop here. I'll post the homework in half an hour on IDEO.